Okay, so welcome. I'll be covering a few items in this presentation related to numerical and relativistic cosmology, though not actually numerical relativity. In particular, I'll be focusing on some recent work modeling the kSZ effect and how this can be useful for constraining physics on ultra-large scales, in particular including relativistic effects. So for anyone watching this who I haven't met before, I'll briefly introduce myself. I arrived as an assistant professor here at Washington University in St. Louis last summer. And before this, I was a student national fellow, a postdoc at York University and Perimeter Institute in Toronto. And while I was there, I worked with Matt Johnson and his group, and they've been especially interested in observations of physics on ultra-large scales using kSZ measurements. As observations on these scales, we expect these can provide us with a way to measure signatures of a variety of new fundamental physics, including especially early universe phenomena, and in particular also general relativistic effects. So I've been interested in particular modeling relativistic effects and have approached this from a few directions. Some of the problems I've been interested in relate to how gravity on small scales can nonlinearly affect physics on much larger scales. And I've often been interested in using numerical relativity simulations for this work. So these provide us both a very high level of precision, but also a high level of confidence that we've correctly and completely accounted for all of our gravitational interactions. I'm not going to be talking about that today, though, so this will be based on work that's at least partly grounded in Newtonian simulations. And there are a few motivations for this. So one of them is that when modeling the Kinetic and Zildovich effect, or the kSZ effect, it's quite impractical to model this from first principles, especially the relativistic contributions, and I'll elaborate on this later on. So the goal is not going to be to obtain fundamental models of cosmological systems, but instead to examine how well different observables can probe relativistic contributions in a more standard, albeit approximate setting. So I'll be discussing some work based on these Newtonian simulations, combining them with linear theory. So work aimed at incorporating linear relativistic effects in simulations, and then thinking about further work incorporating higher order relativistic effects. And so I'm going to focus on published work, but there is some unpublished work, and so for the most recent work in this direction, in particular of including nonlinear effects, I'll refer you to GT on stock. Okay, so I'd first like to cover just some background material, introducing some ideas that'll come in handy later, especially for modeling higher order and relativistic effects. And I'd also especially like to introduce the kSZ effect from a relativistic point of view. Then go through a little bit of detail and additional motivation for why we want these models, and discussing reconstruction a bit. And last, describe some of the details of the simulations we've been working on and how these simulations have provided us with some validation of analytic work, and also where there may still be room for additional modeling. Okay, so I do want to spend time introducing the kSZ effect from a relativistic point of view. I don't want to cover too much in the way of introductory cosmology, but I do want to briefly recap on the CMB itself, in particular as it ties into the kSZ effect. So the CMB, as you hopefully remember, this is light emitted in the early universe. It was emitted as the universe transitions or cooled from a hot ionized opaque plasma to a neutral transparent one. And so locally we observe the results of this as a fairly uniform photon bath. There are small anisotropies in this light, dominated by a couple things, so galactic features and then an overall dipolar modulation. So if we subtract these features, we can see an underlying pattern of these, part in 10 to the 4 or 5 temperature fluctuations. Okay, so there are a number of effects that contribute to these small-scale anisotropies, and these, coincide with different physical phenomena, and that we can interpret in a Newtonian setting. So loosely, the leading effects can be decomposed into a few terms, and these correspond roughly to intrinsic temperature perturbations, or regions that are slightly warmer or cooler than average. There are then similar terms related to gravitational redshifting of photons, so as they leave regions of space they were emitted in. And we call this the Sachs-Wolfe effect. Then additionally, along the line of sight, as photons travel through time-varying gravitational potentials, they can also be redshifted or blue shifted. So then we also have these peculiar velocity terms, and the CMB dipole itself that we observe can be thought of as predominantly sourced by our peculiar velocity. So that is, we can, say, boost to a different frame and significantly remove or reduce this contribution. This is just through a special relativistic Doppler shift. And so this decomposition isn't it's not a gauge invariant interpretation. These effects can be interpreted differently in different gauges. So as an example, what we consider to be the intrinsic dipole rather than the dipole due to our peculiar velocity can change. So as an example, in co-moving gauge, velocities are by definition 0, so there's no local peculiar velocity contribution. And it's also true that different physics can dominate on different scales, and on small scales at least, the Newtonian interpretation is a fair description. But the point here is that the physics I want to discuss today, it depends on both large and small scales, and so we do need to be a little careful about this. In particular, we want to consider all of the contributions to the physical observable, either exactly or at least at a given order in perturbation theory. And so at second order then, there are a number of effects that can appear, and these include effects related to photons traveling along true geodesics as opposed to straight coordinate lines. And these include things like lensing and time delays, things like post-Born effects, as well as scattering. So photons, as they travel to us, can scatter off of electrons. And the kSZ effect itself falls into this scattering category. In general, CMB photons can inverse Compton scatter off of free electrons, and so it's useful to consider the different contributions or terms that show up in this process. And so there are some overall terms that will result in, say, shifted frequencies of scattered photons. These frequency-dependent effects, if you like, include the thermal SE effect. So we can think of that as an increase in photon energy due to electrons having some thermal distribution of velocities. And along with this, there is also the so-called relativistic kSZ terms. So these are higher order frequency-dependent corrections to things like non-thermal bulk velocities of electrons and structures. But there are also terms which preserve the black-body nature of the spectrum. So the low energy limit, we have Thompson scattering. And this contribution in particular I'll refer to as the kSZ effect. So the Thompson scattering cross-section is given on the slide here, and the important thing to note is it's a function of cosine squared at the scattering angle. So this means we're just as likely to scatter photons in forward directions as we are backwards. And so physically, this means for every photon that I scatter out of my line of sight, at least in a statistical sense, another photon should be scattered into my line of sight. So to get a feel for what this means when it comes to observables, we can consider what happens if we have a completely homogeneous universe. So all photons are the same temperature. This means the distribution of photons I observe after scattering won't change due to the Thompson scattering terms. So any photons deflected out of my line of sight get replaced by photons scattered into my line of sight. And because all photons have the same temperature, there's no change. So what does it take to introduce some temperature anisotropy due to Thompson scattering? Well, if we have, say, a dipole feature that's aligned at least partly with the scattering angle, we'll receive information about this dipole amplitude. So we, through the scattering process, can measure the dipole that the electrons observe projected along the line of sight. Okay, so this means the CMB dipole itself turns out, I mean, this is a physical observable at the location of the electron. So it itself is a gauge invariant quantity. The kSZ effect, it's often attributed only to the peculiar velocity of electrons. And so even though this, that might be the dominant contribution to the dipole, but it's not the only one. So take ourselves as an example. So our own CMB dipole can be largely attributed to our peculiar velocity with respect to the CMB. But there are these other contributions, the primary CMB terms we discussed earlier. And if I'm interested in how the CMB dipole looks according to observers separated by a large distance, then the random peculiar velocities that electrons pick up due to small-scale nonlinear processes, that doesn't matter as much. So another important insight is because the kSZ effect it is sensitive to primordial CMB physics. It's also sensitive to physics on the interior of our light cone. So photons that were not originally on a course to us can actually be scattered into our line of sight. So the kSZ effect can actually provide us with a way to at least partly circumvent cosmic variance. So we'll have access to information, not just on our past light cone, but on its interior as well. So this particular point is one reason why it's so difficult to model the kSZ effect from first principles. So in principle, we'd need to keep track of the past light cone at every point on our light cone. And so, such a calculation is really intractable. So we do need to work in some approximate limit. And what we'll end up doing is tying in results from linear perturbation theory into simulations. Okay, so the cumulative temperature perturbation we see from the kSZ effect, this will come from electrons on our past light cone. So we can express temperature perturbations as an integral of the electron number density times this thing I called V. It's not just the peculiar velocity now, though. It's the remote dipole according to electrons, again, projected along the line of sight. And so the relativistic corrections, at least to leading order, those are the primary CMB terms as well. And so if we compute the power spectrum of what these temperature perturbations look like, it turns out they're actually the dominant, at least blackbody contribution to the total CMB power spectrum once you get to L of a few thousand or so. So measurements of this effect, should be measurable by any upcoming experiments with sufficient angular resolution. So if you can resolve L's out there. Okay, so if we can also look at the correlation function of the remote dipole field itself, just to try and gain some intuition for how important these primordial CMB or general relativistic terms are. So we do see some significant modification on very large scales at low L. And so if we're interested in looking for relativistic effects, we can treat this as another signal on large scales. On the other hand, we might be interested in other physics, like some other effects that show up on large scales, and then we might consider this as a bias or systematic. But in either case, if we want to make use of the large-scale information content of the remote dipole field, we'd also like some way to estimate what the dipole field is, given measurements of the CMB and our galaxies, if you like. And so this is one of the aims of different reconstruction techniques. So notably, these techniques result in a noise curve that actually decreases at lower L, so they can be quite useful for measurements on large scales. So in order to reconstruct the remote dipole field, we have a few options. One method is to look at cross-correlations of CMB temperature perturbations with galaxies, which in turn trace electrons. So if we look at the cross-spectra of these, and remember that the temperature perturbations are sourced by the electron-dipole product, we can recognize this as a particular bispectrum. And so if we expand this out and consider different contributions on different scales, the dominant term here ends up being the galaxy-electron cross-correlation modulated by a long wavelength perturbations in the remote dipole field. So one estimator is quite literally just compute the galaxy temperature cross-correlation and then the galaxy-galaxy cross-correlation in a patch of sky, and just divide the two. And so this will determine the remote dipole field, at least up to an overall bias coefficient then. And we'll also be interested in making sure we include additional effects, especially eventually nonlinear effects that might result in some non-zero correlation between galaxies and CMB temperature perturbations. So there are a number of ingredients we've worked on including so far. These have included things like gravitational lensing, making sure the primary CMB itself is modeled consistently with the galaxy distribution, the kSZ effect itself, of course, and then additional noise terms that can stand in as additional potentially contaminating physics. And so again, for some of the potential future effects we'd like to consider, I encourage you to listen to G's talk. So at the level of simulations, how do we properly make sure everything is correlated? So in particular, how do we do this in a volume large enough to encompass the CMB? Clearly it's not practical to run a simulation that both encloses this volume and also resolves details on the small nonlinear scales that correspond to L of 3000 or so. So on large scales, we can rely on just a linear approach and don't worry about accounting for potential correlations between modes. So we'll assume modes have not interacted nonlinearly. So the simulations we run will still run in a volume of order gigaparsec or so, but then we'll be interested in modeling modes also much larger than this. And so for those modes, linearity is still a relatively safe, although still approximate assumption. And so there will be a few operations we can define to help both generate information on these scales and incorporate that into simulations. So we can define a coloring operation which rescales the amount of power in our field by a specified amount. So as an example, if this PC here is a power spectrum of a field, if we take that to be the power spectrum of the field F, and we supply the inverse power spectrum of this field, that'll whiten the field. Or say we already have a white field, we can convert it to a field with a desired power spectrum by supplying a particular PC that we want. And so it's once we have that, it's also useful to define an inlaying operation. And so this operator replaces part of one field with another. So it's going to replace part of some field F1 with field F2. And then the way we add in large modes, we refer to this as a sewing procedure. So the idea will be to whiten some large-scale realization of a field, then whiten a small-scale realization as well, which we're going to generate with an n-body code. And then so the small-scale field into the larger one, and then recolor everything. So if we're in particular interested in obtaining the primordial gravitational potential, and we have the density field as output by simulations, the operation looks something like the second last line here. So we generate some Sonnen density field and subsequently extract the primordial potential based on linear theory. That would generate this field. So the overall, this is where the overall numerical factors and the transfer function out front comes from. So this simplifies a bit for the last line. So we can replace these leading operations by some coloring operation. And so we're just going to color by the primordial power spectrum. Then the ideal will be, given some primordial potential, we can define transfer functions that extract the kSZ contribution or other large-scale contributions to observations. So pictorially, how does this work? So here we can show this idea working in practice using simulation images. So in our small volume, which it's really not that small, it's like a gigaparsec cube, we can run some simulation. And again, we're not especially interested in the precise nature of small-scale power, like what the kSZ or galaxy or baryonic power spectrum looks like on small scales. We're really interested in how that changes from region to region in the universe. So the resolution or small-scale physics, it doesn't need to be perfect, and so emulators or fast codes are all right. So this particular realization was generated using the LP color code, and this provides us with both snapshot information or information on spatial slices, along with particle data on the past light cone. Or if I want to be a little more careful, particle data on like the past null coordinate cone. So then we can use the light cone data to extract halos, information about lensing, or whatever else you like, and the snapshot data for extracting the primordial potential. And these are really the two ingredients we need to put everything together. So in terms of the inlaying procedure, we'll have some whitened field based on n-body data. That's here on the left. So if you kind of squint at this slide and squint at this past slide, and I go back and forth, maybe you can see that. So like the overall power changes, but the features in the field should remain the same in real space. And then the resolution is also lower, since we don't want to simulate the entire observable universe at the resolution of our n-body simulation. Well, we want to, but practically speaking. And so on the right here, we have some random white field. And this is the other ingredient we need for this procedure. So now if I toggle these next two slides, you see that, this small central region changes just a bit. And so here we're putting our gigaparsec box inside some much larger super Hubble volume. Right, and so then on this last slide, here's the final primordial potential on large scales. And so as a demonstration, this procedure works and kind of makes sense. What we should be able to do is subtract off the field we've inlaid and then see only long wavelength modes left over, or modes that are effectively larger than the volume we simulated. And so that's on the right here. We've just zoomed in some so we can see the detail. And so then we see there's no small-scale power in this inlane region after we perform the subtraction, just these large-scale modes. Okay, so once we have the primordial potential, we can go ahead and generate the kSZ contributions. So now these will include contributions from both the n-body simulations, so in particular the local peculiar velocity contributions, like especially the ones coming from nonlinear growth of structure. And we'll also be able to include the primordial contributions to the remote dipole field based on the large-scale potential we generated. So loosely, you can see the two components pictured in the maps on the left, the n-body Doppler contributions on top and primordial on the bottom, and then the sum over to the right. And so if I toggle over a slide and you look at the top left image, you can see the difference between the two. So the primordial effects are indeed modified on large scales here. So on this second slide, we can also see the resulting kSZ temperature perturbations. Recalling that the temperature perturbations are an integral along the line of sight of the electron density times this projected dipole field, we can write down a discrete version of this integral where we just sum over particles. So this expression is, it's been used before to generate kSZ maps, but now we're interested in including primordial terms. So essentially the velocity contribution will be replaced with the full remote dipole. And so, of course, we'd like to include other contributions. So we've worked to include a few of these so far. So we can generate, first of all, the primary CMB using the linear transfer functions combined with the primordial potential that we've generated. Then we can also generate a CMB lensing map using the n-body data in addition. And then last we can generate some additional noise contributions that correspond roughly to some combination of instrument noise and kSZ signal from higher redshifts that we haven't accounted for on contributions on smaller scales that we haven't accounted for in this model. So putting this all together, we get this nice simulated CMB temperature map where everything's consistent, and we've included the kSZ. Right, so then we can test this reconstruction procedure. So I showed kind of a cartoon version earlier of how the reconstruction, how you might perform some reconstruction. So more formally, we would, write down some quadratic estimator or some other estimator and test this process using those. And here I'm showing the results of using a particular quadratic estimator. And on the left, we have the reconstructed remote dipole field from the final CMB density maps out to L of a dozen or so. And on the right, here we have the true one, although only with information from the same out range. So kind of by eye, you can see, okay, these two maps are pretty strongly correlated, especially the large scale features. And the LP simulations we ran did have limited resolution. There's something like 12 80 cube particles in a gigaparsec box or so. We also had other, made other assumptions like the electron distribution perfectly traces the dark matter. So it's also useful to test this sort of reconstruction on other suites of simulations or data that's been generated. And so we've tested this on the web sky mock simulations used for SO as well. And this includes additional physics like baryonic effects, although it doesn't include the relativistic kSZ contributions. And so insofar as the reconstruction procedure is concerned, again, it seems to work. In a future goal, we'll see, be to see how well this holds up, especially in the presence of higher order effects that can contaminate the reconstruction procedure. So to wrap up with a couple of details or advertisements about, how measurements of the kSZ can be useful, and so accurate models are needed. A number of forecasts have come out using Einstein-Boltzmann codes that look at the constraining power of kSZ on different physics. These include things like, modified gravity models. I think, looking at a simple mu gamma parameterization, and also, working to extend that, looking at CMB anomalies, isocurvature, and then of course, looking at general relativistic effects themselves. And so as for the GR effects, we can explicitly try and assess detectability or how they might bias measurement of other physics that can appear on large scales. Here on this slide, I'm just pointing out a few results from this sort of forecasting. So if we're interested in measuring how well we can constrain relativistic effects, what we can do is try and constrain a parameter multiplying the GR terms. And so nominally the value of this parameter, here it's epsilon GR, the value of this parameter should be 1. And then if we ask, okay, what's the uncertainty with which we can measure this parameter, if we can pin the uncertainty down to be less than 1, or ideally much less, then we can claim to have detected GR effects. And then we can also ask about, bias. Again, ask about bias of parameters from other physics. Okay, so for the GR effects that show up just in looking at the distribution of galaxies, there's not a strong case that we'll be able to measure GR effects just using galaxies, but when you look at cross correlations, and especially when you take into account or use information from kSZ, the case gets much stronger. And so, we're looking at potentially a many sigma detection of relativistic effects. And then as for bias, certainly if you're going to get a few sigma bias, which is sort of the bottom right number here, like up to like a 3 sigma bias, if you don't correctly account for all the relativistic contributions, that would be something one might be concerned about. Okay, so, of course, you're only going to get out what physics you put into the simulations. So if there's physics that in reality exists but is missing from simulations, that's an opening for either bias to creep in and lead to some parameter misinference, or possibly, a loss of some otherwise useful signal. So we should, of course, work to include physics from first principles when we can, and if not, then do our best to incorporate as much physics as possible.